Over the last couple of years, the entire trajectory of LLM development by frontier AI labs has been dictated by a single law, the scaling law. We are going to break down how scaling law works, and we're also going to cover the famous debate between OpenAI and Google DeepMind that reshaped the industry. So for decades in machine learning, things revolved around a fundamental trade-off illustrated by this U-shaped loss curve. If your model is too simple, that means your model has few parameters, it underfits. What does that mean? That means it fails to capture the complexity of the data to solve the problem. It's just too simple to actually handle that complexity. By increasing the complexity of your model, by making your model larger, you will eventually get better results. But if you keep increasing the complexity of the model on a fixed data set, at some points, something dangerous happens. Performance plummets. The model starts memorizing noise because your model is simply too powerful for the task and for the data in hand. So it will do the easier thing. The easier thing is memorizing everything that is there rather than doing the hard thing, which is actually learning generalizable patterns. Think about it as you have an exam tomorrow and tonight you were gifted an infinite visual memory. What are you going to do? If you can, you will memorize all the material. Why bother learning the concepts? This is exactly what happens with models that are overly complex for the task and for the data in hand. This constraint existed because of one major assumption. Data was always limited. Human annotation and labeling were slow and widely expensive. AI progress was limited by human annotation or supervision. Researchers were looking for a way to move past this limit. They noticed text is actually a perfect test bed for this. If you hide the next word in a sentence, the text itself provides the ground truth. For example, in a sentence that says the cat sat on, if you mask the next word and force your model to predict math, you're actually doing next word prediction and you're getting all the label data for free. Text was an abundant, naturally self-labeled playground for deep learning, or in this particular case, self-supervised learning. So we turned vast internet corpora into a naturally labeled dataset. Suddenly, data was no longer the bottleneck. Once we unlocked this self-supervised approach, we realized we weren't limited by label data anymore. We were actually limited by compute and scale now. This raised a fundamental question. If you give a transformer model or a deep model more data and more compute, how predictably does it get smarter? To understand this, we look at this fundamental formula for training compute cost, measured in floating points operation, flops. So we have C equal to 6ND. Here, N is the number of parameters in the model, D is the dataset size in tokens, and the factor of 6 represents the computation per parameter per token. So we need 2 flops for forward pass, and we need 4 flops for backward pass. Because compute budgets are finite, every frontier AI lab faces a core optimization problem now. If your budget C increases, how should you split the extra budget between making the model larger, that means increasing the N, versus training on more tokens, increasing your data set? In 2020, OpenAI had an answer for this. They published the landmark Kaplan paper. To model performance, they used a joint power law equation where total loss decomposes into an irreducible entropy E. So this is the loss that we cannot optimize. There is always going to be some modeling error, and that's this. a parameter-bound loss or a parameter penalty, and a data-bound loss or a data penalty. Loss follows a power law decay with n and d. That means it decreases polynomially with either of those two parameters. So plotting loss across various model sizes and data size, the conclusion was clear. The Kaplan paper suggested that model size matters far more than dataset size. According to Kaplan's power law formulation, they recommended that for any increase in compute budget, you should allocate roughly 73% of that increase to model size and only 27% to the dataset size. This finding heavily dictated the first generation of LLMs. Labs scaled parameter counts aggressively, building massive models like GPT-3 with 175 billion parameter or Palm with 540 billion parameter trained on a relatively small amount of text. 2 years later, DeepMind reevaluated this premise in the Chinchilla paper. They discovered 3 key flaws in Kaplan's methodology. First, Kaplan ignored embedding parameters and only considered non-embedding parameters. They also fed the power laws on small models. When you do that, ignoring embedding parameters will actually have a high cost because they will completely skew the mass. And they also used sub-optimal learning rate schedules that artificially penalize longer token runs. Okay, fixing all of that by evaluating over 400 models with properly tuned learning rate schedules, DeepMind proved that data and model size are equally important. So the increased compute budget should be split 50-50 between N and D. So Chinchilla demonstrated that optimal loss occurs when parameter count and token count scale in equal proportion. That will point out to roughly 20 tokens per parameter for training. This revealed that the landmark models like GPT-3 or Palm were actually undertrained, severely undertrained. Parameter heavy, but data starved. Before talking about the modern era, let's actually do a quick recap here. So we had the Kaplan era 2020 and 2021, and then we had the Chinchilla era 2022, 2023. In the Kaplan era, we learned that scale is king. We need to scale parameters aggressively. As a result of that, data got secondary, and we trained this massive parameter-heavy models such as GPT-3 or Palm. In the Chinchilla era, we learned that we need to balance parameters and data, and that's how we can get the best value for the compute. So the models in this era are lighter. They are compute optimal models, such as LLaMA 1 and the Chinchilla model itself. But then people started to realize LLMs do not quite follow the traditional rule of cost measurement in deep learning models. What do I mean by that? Let's take a look at the total cost formula for a second. The total cost of a model is equal to the cost associated with training that model and the cost associated with serving that model. So the cost of training is a function of N and D, number of parameters, and how much training data do you have. And at the inference time, the cost is a function of number of parameters because you have to serve that model, but also the number of queries. How many times you're actually taking an inference from this model? Well, things has changed today. The training cost is paid once, and it used to dominate the overall cost associated with a model. But today, things are completely different. We have the inference cost, which is multiplied by Q, the total number of user queries over the lifespan of the model. When a model such as today's LLM is deployed to 100 millions of users. Most of these models, the popular ones, have to actually serve more than tens of millions of queries every single day. Cost of inference completely dominates the total expenditure. And because cost of inference depends directly on the model size n, every extra parameter in the model makes every single query more expensive. So there is just one way to keep the cost under control and make better models, focusing on more data. This shifts our paradigm from compute optimal or training optimal to inference optimal or deployment optimal. In the modern era, frontier labs intentionally front-load massive training costs. In a way, overtraining these compact models well past the Chinchilla point. This will keep the n small for ultra-cheap, fast inference. This brings us to the three clear generations of LLMs. Under trained era, we have parameter-heavy models like OPT, 175 billion parameter, and GPT-3, also 175 billion parameter. And if you really look at the numbers here, for example, GPT-3 was trained on 300 billion tokens. That gives us a ratio of 1.7x. That means we only have 1.7 token per parameter. Then we have compute optimal era. We have more balanced models here, following the Chinchilla line, like LLaMA 1, 61 billion parameter, which was trained on 1.4 trillion tokens. That gives us a ratio of 22x. That means 22 tokens per parameter. Very much close to the Chinchilla ratio. And then we have eventually the inference-optimal era. That's 2024 to present. Models heavily overtrained for efficient deployment. For instance, LLaMA 3.8b was trained on 15 trillion tokens, an incredible ratio of 1875x tokens per parameters. By overtraining smaller parameters, we get the intelligence of much larger systems at a fraction of the serving cost.